Hi everyone. So today we have Christian Carrick who will be speaking on the homology of BPRN as C2 fixed points.
Awesome. Let me start by thanking Sarah for having me speak here. Thanks everyone for coming to this talk. There we go. So let me say first that this is a project I've been working on with my advisor, Mike Hill and Doug Ravenel. And it's sort of in progress, but I'll try and say, which parts are still in progress and which aren't. Okay, so this computation, the homology of the fixed points of BPRN, is a computation in equidariant homotopy theory. But I want to first just back up and look at some bigger picture stuff as to why we would want to do this sort of computation. So let's start from a hopefully familiar point, which is that if I have a spectrum X, or if you want a space X, then the cohomology of X has this extra structure of being a module over the Steenrod algebra. So here I'm taking mod 2 homology, and everywhere I'll be working at the prime 2. So if I don't say otherwise, then homology or cohomology will be mod 2, and the Steenrod algebra will be the P equals 2 Steenrod algebra. Okay, so this is nice structure. It would be an understatement to say that this is a useful invariant of X. So for example, there's this atom spectral sequence, which has this nice algebraic input involving homological algebra over the Steenrod algebra using this structure above. And this algebraic thing outputs this more mysterious sort of homotopical thing of maps between X and Y. So for instance, if X is the sphere spectrum, then these are the homotopy groups of Y. So this is a really useful structure. One of the things that makes it a little more difficult to deal with is that this algebra A, the Steenrod algebra, is not finitely generated. So it's difficult to do homological algebra in this category. So one of the ways we might try and get around this is by looking at subalgebras of the Steenrod algebra and seeing what they can see. So we'll look at some particular examples that we call the ANs. So these are the subalgebras generated by the square 2 to the i's for I less than or equal to n. So these have some nice properties. For one thing, they exhaust A. So every element in the Steenrod algebra is in one of these ANs. And crucially, A is a free module over AN. But sort of as promised, AN is finite. So finite hop algebras are particularly nice in doing homological algebra over them, mostly because of this property that they're self-injective. So for instance, you can take projective resolutions and injective resolutions by free modules because of this self-injectivity. So that's some sort of useful algebraic properties of that, and we want to exploit that in topology. So one of the ways this might be useful is if I happen to have a spectrum Y whose cohomology is induced from AN. So here M is some AN module, and I induce up to get an A module. And if that's the case, then I get this nice change of rings isomorphism that trades out these X groups in A modules for X groups in AN modules. So this isomorphism is from the fact that the cohomology of Y is induced, and it also uses the fact that A is a free AN module. So in particular, A is a flat AN module. Okay, so as I said before, this homological algebra is easier because AN is finite. So let's look at some situations when this actually happens. So Mahowald and Resk looked at spectra like this in a kind of general way. So they defined an FP spectrum to be a spectrum that's bounded below and 2 complete. And these first 2 assumptions are just sort of to make sure that the atom spectral sequence converges. So the more important thing is that the cohomology of X is a finitely presented A module. They also gave a filtration of this category. So an FP spectrum, so FP stands for finitely presented. FP spectrum is said to be of type less than or equal to n if there exists a finite spectrum F of type n+1 such that the homotopy groups of X smash F are finite. So just some comments that F type n+1, this is in the sense of like chromatic type. So it's a Kn acyclic, but not a Kn+1 acyclic. And this is really not just that this homotopy groups are finite in each degree, but finite in each degree and only finitely many non-zero degrees. Okay, so I actually won't say too much about this second condition as stated, because we'll give a different view on it. Next slide. So the connection here is the following proposition. If I have a spectrum X, which is bounded below and 2 complete, then it's an FP spectrum if and only if its cohomology is induced from AN for some n. So this is the connection to the stuff I mentioned earlier. Here M is actually a finite AN module, and that's because of this finite presentation thing. So this is actually not hard to show. This basically is just the fact that the ANs exhaust A. Okay, and I gave this definition of FP type less than or equal to n. And well, there's a different way of looking at this. So this isn't an if and only if, but if the cohomology of X is tensored up from AN, then it's FP type less than or equal to n. So this is the way that we will think about the FP type. Okay, so FP spectra, these are the sorts of things we're looking for that are going to have these nice atom spectral sequences. So let's give some examples. So on the left here, I have some FP spectrum, and then on the right, we have its cohomology. So this is a really nice list, because you'll notice that not only are these induced up from some AN, but you're inducing up F2. So this is sort of like taking a Hopf algebra quotient. So that's what this notation A mod mod AN means. And so these computations tell us that the atom spectral sequences of these spectra on the left are very nice. Okay, but this is kind of a special thing that happens for n less than or equal to 2. So unfortunately, the sort of obvious pattern where you would want something whose cohomology is A mod AN doesn't continue. So for instance, if you had some spectrum whose cohomology was A mod A3, then what you could do is take the 2 to the n+1 skeleton of that spectrum, and you'll get a finite spectrum with 2 cells connected by a square 2 to the n+1. So in algebra, this is an extension of F2 by itself over the Steenrod algebra. And if you had this complex, then it would basically tell you that X1 class survives the atom spectral sequence, and that's equivalent to the existence of that Hopf element. So for n greater than 2, we just don't have this. So maybe we still have some spectra whose cohomology is tensored up from AN, but it won't be just tensoring up F2. So let's give an example of something that does work at all n. So I can look at these truncated Brown-Peterson spectra. So BP is the Brown-Peterson spectrum. And I form this BPN just by killing off the VIs for I greater than N. And these turn out to be FP spectra. So, and the height corresponds to the chromatic height. So this is just a computation. You compute the cohomology and you observe that it is tensored up from AN. And then that gives you this. Okay, but these sort of aren't great. They're not really doing what we want FP spectra to do for us. I'll say a bit more about that later, but let me just remark here that we don't really have a lot of examples of FP spectra for N greater than 2. We have these, but these aren't great, as I said, so I'll say more about that. So what are these FP spectra expected to do for us? So first of all, just the thing I mentioned earlier, they make these atom spectral sequences much easier to compute. And there are some other things that they do, and most of these are sort of consequences of this atom spectral sequence fact. But I'll just point some of them out here. So in this paper where Mohoald and Resk define FP spectra, they study some very general properties of them, and they show that the category of spectra of FP type less than or equal to N has some kind of duality in it. So this is really nice because most FP spectra are not finite. In fact, I think all FP spectra are not finite. And typically we only expect some kind of nice notion of dualizability for finite spectra. So somehow there's something like that available here due to the fact that the cohomology is finite in some sense. So this is a useful duality that we can look at. And one of the main motivations they had in studying these was that you can use these atom spectral sequences to construct a different spectral sequence which computes the homotopy groups of the finite localization of X. So this is a way we can test the telescope conjecture when you have an FP spectrum. So another place these come up is this theory of EONs. So these are supposed to be higher height analogs of connective K theory KO. And we don't have a family of these for every N. There's sort of conjectural spectra that are supposed to satisfy some certain properties. And one of the main things that we expect of them is that they would be FP. So that's another place where these come in. Okay, so on to the actual example in question. I'm going to give some brief background on equivariant homotopy theory. So Fuji and Landweber defined this genuine C2 spectrum MUR. So this is called real Bordisson theory. And it basically comes from observing that this Thom spectrum MU has a complex conjugation action by C2. So this gives us a C2 spectrum MUR. And there are certain ways in which MUR behaves a lot like MU. So since we're working equivariantly, we have this generalized notion of homotopy group available, where instead of mapping in from Sn to MUR to get pi n, I can map in from a representation sphere, like the regular representation sphere, S rho, and get a ROC2 graded homotopy group. So if I look in the degrees that are integer multiples of the regular representation, then the homotopy groups of this equivariant spectrum turn out to coincide with the non-equivariant ones. So that's really nice because we know that the homotopy groups of MU are this Lazard ring related to formal group laws. So basically this is going to allow us to make these kinds of formal group theoretic constructions that we do non-equivariantly in C2 spectra using MUR. So for instance, you can construct a BP here. So in the same way that you construct BP non-equivariantly, you can do that with MUR. And so this is some spectrum BPR who you can think of as a BP with a complex conjugation action. And just like with MUR, in the right degrees, the homotopy groups of this BPR agree with BP. And so we have these equivariant lifts VI bar of the VIs, and we can cone them off just like we do with BP to get a BPRN. So again, this is like some kind of BPN with a complex conjugation action. So one of the reasons that these theories are of interest is that we can take their C2 fixed points. So we can take the fixed points of BPN under this complex conjugation action and see what we get. So at small heights, this is a familiar family of spectra. So in the middle, I have sort of alternative equivariant names for the particular BPM. And then on the right, I've written the fixed point spectrum. So already this list over here is looking pretty good. Instead of TMF at height 2, we have something called TMF03. And this is some sort of TMF spectrum of level structures on elliptic curves. Okay, so maybe this is a good idea to consider these at higher heights. So one of the reasons that we might want to do that is that this BPRN theory sees a lot more than BPN. So in particular, BPN doesn't detect anything in the homotopy groups of spheres in positive degree. And the BPRNs do. So there's this paper of Guchuan Li, Danny Shi, Guojing Wang, and Zhou Zhu, where they show using the C2 atom spectral sequence that, that the fixed points of BPRN detect quite a lot of classes in the homotopy groups of spheres. So these theories are seen a lot more. Okay, so if we want to know whether they're FP spectra, then we would want to compute their homology or their cohomology. So I'll kind of be switching to homology now, but the story is the same. So the way we do this is using this very simple proposition that turns out to be really useful. And what it says is that if I have some G spectrum, Y, and I smash some non-equivariant spectrum with the fixed points of Y, then I can regard that as the fixed points of some other G spectrum. So here, this I star X is just X with trivial action. Okay, so let me give a proof of this. So this I star functor, which gives a spectrum a trivial G spectrum action, is a symmetric monoidal functor, and it's left adjoint to the fixed points. So formally, I have some natural map like this, where I use the fact that I star is symmetric monoidal. And then over here in the right smash factor, I'm using the co-unit of that adjunction. So that gives us an adjoint map from X smash YG to this fixed point spectrum. And it's natural, so I can think of this as a morphism of homology theories and check that it agrees when X is the sphere. When X is the sphere, it's just the identity map of YG. And then crucially, both sides commute with colimits in X because G fixed points commutes with colimits. So this is a very special property of the genuine fixed points functor. So if you're familiar with the homotopy fixed points functor, it doesn't commute with colimits. So we don't have something like that for the homotopy fixed points. Okay, so the point of this for our purposes is that it tells us how to compute the homology of this fixed point spectrum. So the homology of the fixed points of BPRN is going to be the homotopy groups of this smash product with HF2. And this proposition tells us that we can compute that instead as the equivariant homotopy groups of this C2 spectrum. Okay, so maybe this seems like a bit backwards. We're trying to do this non-equivariant computation of the homology of this fixed point spectrum. And we're sort of working our way back into C2 spectra. But the point is that we don't really understand this fixed point spectrum. What we do understand is BPRN as a C2 spectrum. And so if we can put things back into the equivariant world, it's actually a place where we can understand things better. Okay, let me see how I'm doing on time. I'm doing very well. Okay, so let's see how we might approach this computation using that equivalence that I just mentioned. So I want to back up first and do the non-equivariant computation. So how do we compute the homology of BPN? So I said in the beginning that they were FP spectra of type less than or equal to n. So where does that fact come from? Well, what we know about BPN more easily is its homotopy groups. So by construction, you took BP and you killed the higher VIs above height n. And so you know for free that the homotopy groups look like this. So as a general kind of approach to something like this, if you know the homology of a spectrum, then you can compute its homotopy via the atom spectral sequence. But we're in the opposite scenario where we know the homotopy and we want the homology. So one way you can approach that is to use this Atiyah-Hirzebruch spectral sequence. So over here, the E2 page is the homology of HF2 with coefficients in pi star x, which you know, and then it converges to the homology of x. So let's explore that with x being BPN. So here our E2 page looks like this because BPN star is this. And I'll say what happens in the spectral sequence. So first of all, this E2 page is the homology of HZ with F2 coefficients adjoined the VIs. So the homology of HZ is this, and I mentioned this in the beginning in cohomology notation. It's the same thing, so we just took duals and the tensor became a cotensor. So that's our E2 page, and we need some kind of input to see whether there are differentials. And all we really need is to know that VI is 0 in homology. So and this is just something you know from formal groups, for example. So since VI is 0 in homology, then the thing this is converging to has VI 0. So something has to kill this class VI. And you just look at what could do it, and basically this is the only thing that can happen, and you get these differentials. Okay, so after you do this computation, that leaves you with the homology of BPN, and now I've just written it out explicitly. You can check that this is cotensored up from AN star. But basically what happened here is every time we had a differential on a zeta I, then because of the Leibniz rule and the fact that 2 is 0 in the spectral sequence, that makes its square a cycle. So that's why we see these squares here. And then there was no differential on zeta n plus 2 because there was no Vn plus 1. Okay, so that's actually a pretty slick and easy computation. And we're going to try and do that same sort of computation equivariantly. But sorry, let me back up first and say a bit about the Atiyah-Hirzebruch spectral sequence. So usually the way that you construct the Atiyah-Hirzebruch spectral sequence is by taking a cellular filtration of your spectrum Y, and then that gives you a filtration of the X homology of Y. So there's a dual way of doing this, where instead of filtering Y, you filter X by its Posnikov tower. So what we've drawn here is just the Posnikov tower of X smashed everywhere with Y. So let's look at some of the fibers in this tower. So the homotopy groups of this are the homology groups of Y, with coefficients in the homotopy of X. And that's what we know the E2 page of the Atiyah-Herzberg spectral sequence to be. So that's sort of why they coincide. Okay, so, well, the reason I want to consider this approach is that equivariantly, we have a nice analog of the Postkopf tower with the slice tower. So let me just give an example of a slice tower. So first, I'm just looking at the non-equivariant Postkopf tower of BP1. So BP1 has these homotopy groups, and so that tells us that the Postkopf tower has this description. So the fiber at level 0 is just a Z, and then we have the class V1 and then the class V1 squared, and so on. And so that's what the Postkopf tower of that looks like. And equivariantly, the slice tower is the same for BPR1, where you're just remembering the group action. So the V1s became V1 bars, the Z's became this Mackey functor Z, and the 2s became rows. And that's just because the underlying action that you're not really remembering in this picture actually was had some sign representations in it. So that's what this row coming in place of 2 is. Okay, so we computed the E2 page of this, and it's a little bit complicated, mostly just because of the ROC2 grading. So if you're familiar with computations like this of the ROC2 graded homotopy of Eilenberg-MacLean spectra, then you might remember that there's sort of 2 parts to that. There's this area called the positive cone, which is nice, and then this area of the homotopy called the negative cone, which is not so nice. And we sort of always hope that we can ignore the negative cone if possible, and that does turn out to be the case here. So this positive cone part of the spectral sequence has a little bit nicer description. And in fact, it looks almost the same as the non-equivariant BPN E2 page. We have this homology of HC, we have our VIs, and then sort of the equivariant part is just these 2 equivariant classes A sigma U sigma coming from the homotopy of HF2. Okay, and this part of it isn't the whole spectral sequence, but it's enough to know what happens in the integer stems. That's all we really care about, because we want to know what the homology of this fixed point spectrum is. And that's the integer stems of this. Okay, I'm going much faster than I expected, so I'll just kind of pause and see if there are any questions, anything that anyone wanted me to say more about.
Could you clarify which construction of genuine fixed points you're using?
So the way I would think about it is just that it's defined as the, where did I do this? Right here. It's just sort of defined as the right adjoint to this push forward. Yeah, so I guess if you're working in like orthogonal G spectra, then this genuine fixed points functor is actually taking the fixed points space by space in the spectrum after you've like turned it into an omega G spectrum or something. But yeah, I would just, for me, I'm just thinking of it as this adjoint.
Okay.
All right. If there are no other questions for now, I'm just going to move on to the statement of the main theorems we have so far. Okay, but first I'm going to kind of do this computation in a simple case to see how this looks. So let's take the n equals 1 computation. And as a reminder, when I take the fixed points of BPR1, I get KO. And this is because BPR1 is this KR theory. So a T is KR. And so basically what's happening is you took the fixed points of KU under complex conjugation, and that left KO. And that's sort of what we would expect. All right, so here's what its E2 page looks like. So this is just the homology of HC, and I've just written it out in terms of these zeta I generators. And that converges to this equivariant homology. Okay, so there turn out to be differentials in these spectral sequences. And as before, we kind of argue that they have to exist because something has to kill a certain class. So in this case, the class A sigma V1 bar detects the element eta. And that follows from this paper I mentioned earlier, which determines the Hurevich images of the BPRNs. So since it detects eta is 0 in homology, in the homology of anything. And so in particular, eta has to die in the spectral sequence. And for degree reasons, there's only one possible differential that can do that. And it's on the class zeta 1 squared. Oops. So there are more D3s, and these come from the fact that this spectral sequence is a spectral sequence of comodules. So I can expand the coproduct formula for zeta 2. And since D3 has to respect this comodule structure, I can sort of predict what D3 of zeta 2 is supposed to be. And it turns out to be this class U sigma V1 bar. So if you look at what happened here, basically we killed off everything in integer degrees that didn't come from the dual Steenrod algebra. So I can check after these two differentials, all I have left is this. And as I mentioned at the beginning of the talk, this is the homology of KO. So this looks right. And you can check that this is all that happens in the spectral sequence, at least in integer degrees. So that's a relatively quick computation of the homology of KO once you have this spectral sequence set up and using the slice filtration. Okay, so things get a little more complicated at n equals 2. So first, just a reminder that this spectrum at height 2 is TMF03. So our spectral sequence looks like this. Now we have V1 bar and V2 bar. And these are the differentials we see. So we have the same D3s as before. And then we also have D7s. So I've written these D7s in terms of these classes X1 and X2, and I haven't defined those. But I'll say a little bit more about them in a second. And then these are all the differentials. So, computing homology of these differentials is quite a bit harder than in the KO case. But that's one of the computations we've done. So this is what we get. So we get that the homology of this TMF03, which is this BPR2 fixed point spectrum, is co-induced from A2 star. And so this is the sort of equation we were hoping for to tell us that this is an FP spectrum. And in this case, we actually worked out exactly what M2 is. So it's this A2 comodule. So remember, A2 has square 1, square 2, square 4. So that's what we're seeing here. These lines are square 1, these are square 2, and these are square 4. So this is, a little bit bigger than the homology of TMF. So with TMF, this M2 would have just been F2. But it's still relatively small and computable. And so this tells us, how to compute the atom spectral sequence of TMF03, for example. Okay, so when n is bigger than 2, unfortunately, things are harder. But we were able to figure out a family of differentials. So the differentials I mentioned before have higher height analogs. And this formula I've written here is probably indecipherable, but the main point really is just that we have a nice explicit formula for a family of differentials in the spectral sequence. So in the sort of patterns we saw in lower cases with these D3s and D7s continue to happen, and we're able to control those differentials. So as for the extent to which this is still kind of an in-progress project, one of the things we don't know is that these are all the differentials in the spectral sequence. So so we actually know that they're not all the differentials if you consider things that are happening outside of integer degrees, but we expect that this is it in integer degrees. Okay, so let me state the main theorem then. With these differentials and some other things we know about the BPRNs, we're not able to finish the computation of its homology explicitly, like I gave for n equals 2, but we're able to know enough that the spectrum is FP of type less than or equal to n. And I will stop there.
All right, so let's thank our speaker. Are there any questions for Christian? So all of the differentials you have in the integer graded case, these are all from deducing, well, from knowing that something has to be 0, so differential has to exist, and then there are reasons this specifically has to be the form, or are there other reasons as well?
So the argument is similar. Like there are sort of two ways to get these differentials. So, well, after n equals 3, or n equals 2, sorry, it becomes harder to predict differentials just by saying that certain classes have to die, just because we don't have those hop elements. So the approach that we use for those is basically we know that there's at least one differential on this page that has to happen, because we know the differentials in the slice spectral sequence for BPRN. So, so just by pushing forward those differentials, then we can predict at least one differential on each page. And then we can use the fact that it's a map of co-modules to predict a bunch of other differentials that have to happen. So that's one way that you can do that. And we have another way, which is to just look at the geometric fixed points spectral sequence. So when you invert a sigma, you know what it has to converge to, and so the spectral sequence can only go a certain way, and then you can use naturality to predict differentials like these. But yeah, so yeah, at higher heights we have to sort of come up with a different approach. Yeah, thanks.
And then are there in the low dimension, in the low height cases, do you know all the differentials, including in the non-integer graded portions, or are there no examples in which you know all of them?
I would say the only one that we know for sure that I'm aware of is n equals 1. And yeah, outside of that, there's just a lot of weird things that can happen with the negative cone. So in the n equals 1 case, there turns out to be a D5, which kills V1 bar squared. And so we didn't really expect this at first because we were just looking at the positive cone case, but that's something that you sort of have to worry about, because even though it's a differential coming from the negative cone, it's hitting the positive cone. And so it kind of messes with things. But yeah, I would say the only case we know 100% is n equals 1.
Are there any other questions for Christian? Okay, let's thank the speaker again.